right, so kind of talk about the same thing we talked about yesterday. In the first class yesterday, we didn't get through as far as you guys got through, so we talked a little bit more about that today. But if I just want to go back to this situation where, if you remember, we had a test of 4 test takers, and they scored individually a 2, a 4, a 6, and an 8 on the test. And that's the population. Okay, now a lot of times, like we said yesterday, we don't know the population, but this type of problem is allowing us to at least see some data about a population and then go through all of these calculations of the sample means. And because we do know data about the population, make some comparisons that allow us then in other problems where we don't know what the population looks like, we can still make valid conclusions because of what we've seen in questions like this. And I'll kind of explain that again. It's kind of, I think, hard to think about, but with specific examples, you might be able to understand that. So here we have a population mean of 5. In most situations, like I said, we don't know what the population mean is, but for this problem, we do, okay, which is going to be able to establish a nice relationship for us. We went through and we found the standard deviation. The one thing about standard deviation is that because it's a population, we're dividing by capital N. If you remember back to chapter 2 when we did standard deviation by hand, if it was a sample that we were taking and doing the standard deviation, that was N minus 1. But because it's the population here, it's sigma, it's going to be capital N. And we got 2.236. And we also could have done that in Excel here. All I did is I typed in the scores of 2, 4, 6, 8 here. And then in this box, I just typed in standard deviation of P, which is population, and then just highlighted those 4 boxes, and it does that calculation for us. Okay. Bless you.
Thank you.
When we graph these scores of 2, 4, 6, 8, it becomes a uniform distribution, which right now we don't know much about finding standard deviations and that sort of stuff and probabilities with uniform distributions. Okay, we would like our distribution to be normal. So what we end up doing is taking sample sizes of 2. So we're taking 2 test takers at a time, or 2 test scores at a time, and creating a sample of it. Okay, so kind of the idea of, if I have 4 test papers here, and I just blindly pick 2 of them, record what they are, put them back down, blindly pick 2 more, record what they are. Does that make sense? And that is randomly creating these possible samples. We have a sample of a score of 2 and 2. So the idea is that you could, basically when you pick the first one, you put it back in before you pick the second one. So you could pick the same object 2 times, or both times. And then we find the average of those 2 scores in that sample. So 2 plus 2 divided by 2 is 2. Then we do it with 2 plus 4. Okay, 2 plus 4 is 6, divided by 2 is 3. So we do that all the way through with all our potential groups that could be made by doing that. And these columns become what we call our sample means. Okay? Now, because those are individual values that represent the sample, they are a distribution. We call it the distribution of the sampling means. We can, essentially what I mean by that is we can create a frequency table and then graph that, okay? So when we do a frequency table and graph that information, remember that the individual test scores were uniform, but when we graph this frequency of the sample means, what we end up with is something that looks like that, which if we insert the normal curve, that is symmetric, and we can then use our z-score knowledge that we've accrued in section 6.1 and 6.2 to attack questions about the sample means. Okay, so we could ask questions like, what is the probability that the sample means was less than 3, or less than 2, or less than 4? Okay, which is a nice thing for us to be able to do eventually. When we take the mean, so this symbol here is mu, which refers to the mean, okay? Now we use a subscript of x bar. So we read this as the mean of the samples, okay? The mean of the sample means, okay? So these were my sample means. I got 16 of them, okay? And this is then the mean of those 16 things. So the mean of the sample means, so I'm gonna add these all up, I add these green numbers up and I get 80. There's 16 of them, so 80 divided by 16, this average or this mean of the sample means is ending up to be 5. Well, what does that tell us? If we go back up to one of the properties we said earlier yesterday, was that the mean of the sample means is the same as the mean of the population. Well, we knew the population. And this is what I was talking about at the beginning of class. We knew the population, so we were able to find that mu that we usually don't know. Does that make sense? So in this situation, we're able to, because we know the population, we're able to convince ourselves that, yeah, when we do the mean of the sample means, and we get 5 there, and then we do the mean of the population, and we get, oh, I won't highlight that, when we get 5 there, okay, we can see that that connection that the mean of the sample means is the same as the mean of the population. So what does that tell me? Later on in other problems, when I cannot determine the mean of the population, it is unknown. If you can find the mean of the sample means, then you can make the connection that you now do know the mean of the population. Does that make sense? Okay, so let's say that we're looking at all adults back up to this question here at the beginning of 7.1. Okay, we're talking about all adults in the world. Okay, there is absolutely no way that we can determine the mean of that population of triglyceride levels of all adults across the world. Okay, but what we can do is we can take a bunch of samples, find the means of those samples, and then find the mean of those sample means. Okay, which would be mu sub x bar. And once we find that value, then that is going to be identical to the population mu, which is the mean of all adults in the world. Does that make sense? Which would be something logistically we could not find or know initially. Okay, so that's one of the key properties that we're going to gain from this process. We also then said yesterday that if I'm trying to find the standard deviation of the sample means, standard deviation, and then the subscript again of x bar, so that talks about sample means, so standard deviation, sample means. It is the same thing as sigma, which is the standard deviation of your population, divided by square root of n, where n is how big your sample size was. So when we did this yesterday, we were talking about, I went through and I found my sample, I found the standard deviation kind of the long way of our sample means, okay? We listed what all our sample means were, all 16 of them. We subtracted from it the average, so x minus mu. And then we squared that, so we got x minus mu squared, so those are our deviations squared. Sum those up and you get 40, okay? So back to this formula right here, okay? That 40 is the summation of these 16 different deviations, okay? Capital N is how many samples we had. We had 16 of them. So this would have been 40 divided by 16. Okay, that ends up giving us, I believe it's 2.5 as a decimal, but then when we take the square root of that, it gives you 1.5. Okay, 1.58. That's a long process to find the standard deviation of sample means using that approach, but it works. And that's the formula from chapter 2 that we worked a while back. What the central limit theorem is telling us is that we can actually shorten that a little bit if we know sigma, which we know the standard or the standard deviation of the population, which we knew that was the 2.236 number that we came up with up here. Okay, now we still have to calculate that, but would you rather do 4 deviations and do those 4 sums, or would you rather do 16? Rather do 4, wouldn't you? Okay, so that standard deviation, even though we can't kind of circumvent the formula altogether, we can make it simpler for us in regards to the amount of work that we have to do. So we're going to get that standard deviation to be 2.236. And if we divide that by the square root of n was 2 because that was the sample size that we were taking here. Okay. And if we do that, I'm going to show you Excel up here. I'm taking G2, which would have been this standard deviation of the population, so that's the sigma, divided then by the square root of n being 2. That number right there, is that the same as that number right there? Okay. Now there is a little bit of difference out to, you know, that decimal place right there, and I think if I just format these two the same way, I think the cells are formatted differently in regards to rounding, but they're the same. Okay. Which is a nice thing. That should shorten things up for us if we can use this, because most of your problems that we're going to see right now, they're going to tell you what the population standard deviation is. Okay, so instead of doing all of this work right here, if we know that and we know how big our samples are, it's going to be so much easier to find our standard deviation of our sample means. They call it the standard error. That's going to be a lot more efficient. Okay, so that's kind of the nuts and bolts of what we did yesterday. That gets us to actually introduce formally what the central limit theorem is. Okay, so central limit theorem says as the sample size n increases. Okay, so like in the last one we had 2. Okay, in the initial introduction question with triglyceride levels we had n to be 30. But as that number increases without limit, okay, so as much as we can get, as big as our samples can be, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. Okay? So what that means is the more objects I have in my sample as I'm trying to find my sample means, the more objects that are in there, the more normal that sample means distribution becomes. Okay? So as previously shown, the distribution will have a mean mu, standard deviation of sigma divided by square root of n. Let me show you a kind of visual of what this is. Now, I like this, but it's kind of hard to read from your seats. But this yellow thing right here, this is a distribution of some type of data. So this is representing a bunch of data values. I wish this had like a number line on it so you could actually see values or whatever. But we can change that distribution. Okay, I can change that distribution just by changing these parameters of alpha and beta. So this would be, that kind of looks like a square root function. This looks like an exponential distribution. Okay, you can get, you know, a skewed left distribution. We got a skewed maybe to the right distribution. Okay, we can do something kind of like that. So we get some weird distributions to occur, and it doesn't matter the distribution. Okay, so let's say that we start with that distribution. What's going to happen? What this applet allows us to do, and I'm just going to choose a sample size of 2. Sample size of 2. So what's going to happen is that this program is going to randomly choose values or data values, data points out of here. It's going to drop them both down, and then you're going to see an animation where there's two bubbles. Okay, you see how those two dropped down and came back to get together? When they come together, what they're doing is they're saying we're going to take the sample size of 2, and we're going to merge them together and find their average. Kind of like when we took a score of 2 and a score of 4, merged them together, got 6 divided by 2, gave us 3, right? So when that's merging together there and then dropping down here it says count. So basically they're saying whatever that average was, we're going to count it in a histogram. That's why I wish there was a number line here to show you that maybe that average was maybe 3, okay? But it's saying that of our sizes we've taken, the data values we've taken, 100% of them right now fall at that value, okay? Because we only took one sample, right? Does that make sense? So we can keep doing that individually, keep dropping them down and counting them, averaging them, and then counting them, placing them where they belong, okay? And right now we see that with a small sample size, this distribution it kind of looks uniform, okay? What happens though is that as we increase our sample size, Okay, let's just go to 10. So what's going to happen here is instead of 2 balls falling out of that yellow, it's going to be 10. Okay, so we're going to take 10 values, maybe 10 adults in the triglyceride levels, and then they're going to add those together and average them, and then that's going to drop down and be counted down here. So when we do that, you see those 10 merge into that, right? Then we do it again. Keep doing it. Okay, so as I do, I can change this draw. So instead of clicking this button one time and it just dropping 1 down, I'm going to actually ask it to do, 10 at a time. Okay, so that looks a little bit, I'm going to put the theoretical curve in there. Okay, it's starting to look a little bit normal, right? Okay, but it's still a little choppy. So let's go ahead and increase the sample size a little bit further. And let's increase the number of draws that it does through 1 click to go to 30. So this is saying 15 people in each sample, and this is saying we're going to take 30 samples. Okay, so we have like 30 X bars here. If I sample that, okay, does that look a little bit more symmetric? Fits that curve maybe a little bit better, right? Okay, now we might have some, this one here and that one there kind of look like they may be out of position a little bit, but the idea is, okay, well, let's take more samples. Okay, and if we keep doing this, so right now it's continually, as I keep clicking this, it's continually adding to the last one. So I've gotten, I've clicked this maybe 4, 5, 6 times. So we've getting, upwards of 400, 500 different samples in here. Isn't that eventually, the more samples I get, getting and fitting that curve much better? So that's what the central limit theorem says. No matter what your distribution looks like up here, okay, no matter the distribution, as we start fitting it, it's going to fit that normal curve. The more samples we get, it's going to fit that normal curve better. Okay. Now, what we're going to actually find out, and I wish that this applet would have this, is that size of 15 is it's okay. But generally, when we talk about the central limit theorem, we want that number to be at least 30. Okay. So we'll talk about that here in a moment. But it says the central limit theorem, or sorry, when the sample size is sufficiently large, the central limit theorem can be used to answer questions about sample means in the same manner that a normal distribution can be used to answer questions about individual values. Okay. So previously we would ask, like, let's talk about like the age of you guys and days. I could ask, what's the probability that I randomly choose one person and their age is less than 3,000 days. Okay, and we figure that probability out based on knowing your guys' mean, knowing that individual 3,000 and you z-scoring it and going through my normal distribution probabilities. What this is going to allow me to do is say, okay, if we know your age is, what is the probability that I take a group of 4 people and their average age is less than 3,000? Does that make sense? Okay, so now I can ask these questions about groups or samples instead of just individual values. The only thing that happens in doing that is that we have to augment the z-score formula just a little bit. Okay, sometimes you see it written this way, which people start to think, well, that's completely different than what we normally are used to with a z-score. But it's really not, because what we do with a z-score, I'm just going to write the z-score formula here for an individual value. So the z-score is always x minus mu over sigma. Okay, so an individual value or data point out of a population is that. Okay, well, now this x, instead of individual data value, is now the mean of a sample. Does that make sense? Okay, so instead of asking what is instead of 3,000 being the value for one person, maybe 3,000 now is the average of 4 people. Okay, mu is still mu, but now sigma here, remember this was sigma for the population, We now want sigma for the sample means, okay? Well, that was the formula we talked about previously, that sigma, or standard deviation for the sample means, is sigma divided by radical n. Well, we know that is also the same thing as standard deviation sub x bar, sigma x bar. So you'll see this one written in textbooks a lot, but I prefer this one because that one is really the same format as x minus mu over sigma. We just got to remember x bar is a sample mean, and sub x bar means we're talking about the sigma, or the standard deviation of the sample means. Okay. Once we find that, we get that data value, and we'll see some examples of this tomorrow. We're not getting any examples today. But once we find that, we treat it just like a normal z-score. Okay, we take our z-chart, z-table, or we can use Excel or whatever, and we can find those probabilities just like we did in 6.1 and 6.2. Okay. The only thing that we have to talk about is if sample means are taken from a normally distributed population. So we know, maybe we've got all the data from the population and we plot it and we know it's normal, okay? Or maybe we run a hypothesis test later on and we know that the data is normal. Then that means that no matter what I do with the sample means distribution is always going to be normal. Does that make sense? So the idea was, going back to this here, this distribution we didn't know anything about, okay? It was not normal. But when we take the sample means distribution, it does become normal. If I have a population that looks like this, okay, this population looks maybe like that. That looks normal, doesn't it? Then I am guaranteed that when we do this, that the sample means distribution will be normal, no matter how big my samples are. So I can take samples of 2, samples of 3, samples of 4, it will be normal, okay? If sample means are taken from a population that is not normal, or a population that you don't know about, okay, yet you have no information about whether it's normal or not, then what you want to do is make sure that your n value, your lowercase n, your sample size for each sample is greater than or equal to 30. Okay, that's a rule. I'm gonna call that a rule of thumb or a guideline because it can sometimes be broken. Okay, but for our purposes and introductory statistics, we want n to be greater than or equal to 30. So this population up here, when we did this, we have no idea about the population of adults and the triglyceride levels of whether that's going to be normal or not. We have no idea. Could be normal, could be hypergeometric, could be exponential, could be Poisson, don't know. Okay, it could be a just a nasty looking distribution that maybe looks something like that. Okay, we just don't know. But if I use my sample means to be 30, I'm guaranteed that when I find the distribution of the sample means, my sample means will be normal. Does that make sense? So we have to have 30. It doesn't mean that if it's less than 30, it's not going to be normal. So if I have maybe a sample mean or a sample size of like 20, it doesn't mean it's not going to be normal. It's just not guaranteed. Does that make sense? It's like when we say that, and if I give you a triangle in front of you and I tell you, you don't know that the two sides are congruent. Doesn't say it's not isosceles. You're just not guaranteed that it is isosceles. Does that make sense? I give you a triangle, I tell you know nothing about the sides. It could be isosceles, you just don't know. Does that make sense? Okay. So being less than 30 does not say it will not be normal or the distribution of sample means will not be normal. We're just not guaranteed it. The idea, and I'm not going to get too much into it right now, is that when we talk about a population, we could probably argue that no population is going to be exactly normal. Okay. But they're going to be close enough, and we're okay with it being close enough in our applications. Does that kind of make sense, what we're doing here with the central limit theorem. Tomorrow, what I'd like to do is get into these examples and just run through these examples. They're not extremely difficult as long as you're able to recognize what is mu, what is my population mean, if they provide it, what is the standard deviation of the population, and then run through z-scores just like we have been in 6162. Okay, so we'll do 3 or 4 examples tomorrow, but that's all I've got for you today. No new homework. Actually, we're going to do that. We're going to do that Monday. Tomorrow, I'm going to give you I forgot tomorrow's Friday. I'm going to give you a quiz tomorrow over 6162, just finding z-scores and then telling me whether you can determine what the probabilities are from those z-scores. Okay? Shouldn't be anything that is extremely complex. If you're able to do the last 2 homework assignments, you're going to be okay with tomorrow's quiz. Yeah.